Hi, I'm James. I'm Principal Scientist here at Vertical, and what I want to talk to you about today, we've got the title Strongly Typed Data for Machine Learning. So what I want to try and explore is how does typing on your data affect the world of machine learning? What does that really mean? What are we trying to achieve there? So let me lay out how I see the typical workflow in an ML project, perhaps a small scale one, and heading up to large scale depending on how you swap these components out. We're typically going to start off with some kind of data source that is almost ubiquitously tabular at the moment, almost always. And the way that, so what we're going to find is that we've got a few tables that are linked together in some way. And in this example, I've got, for example, table T, which has some row, which is an example we're interested in, that actually has four relations. It's related across to A and B. So we've got A1 and B1, for example, A1, A1, A2, B1, B2 as the other examples in different tables that it's related to. And the trouble we face is that when we try and actually build the features that we want to learn over as input to our ML pipeline, we are faced with a couple of ugly options for how we go about doing that. The first is, okay, I want to represent this one example that's from table T, and so I'm going to split out the relations that it has into two other parts of my feature vector. I'm just going to stack them all together. I'm going to say, okay, I've got T, and then I've got A1, A2, B1, B2, all of them represented numerically with some feature vector that we can build up, and I just stack them. But this adds an extra problem for me, because now it matters the order in which A1 and A2 are added to this stack. Now suddenly my neural network is going to pick up if I've got any kind of bias as to how I order those two examples. It thinks that actually it matters which order these are in. The same goes for B1 and B2. So this isn't really nice. What we also see is that if I just stack these feature vectors that I've built up like this, then I'm gonna, if I have more than two relations or less than two relations, I'm either going to end up with padding my vector out with zeros, or I'm going to end up with a really long vector. And if I hit having a really long vector, then I start to suffer the curse of dimensionality in machine learning, where we've got too many dimensions to work in. So this isn't really nice. My other alternative, and I'm sure there's others besides, but that you can start to see how inherently this ends up being kind of ugly, is that I repeat T over and over again, and I leave one placeholder for some relation of type A and some placeholder for a relation of type B. So that may be that I end up with neither, in which case I just end up with one big padding of zeros, or I have to do all the combinations of A and B, and I end up with a lot of repetition of the one actual example which is present, which is T. What we're seeing is that really I'm lacking a way to actually talk about the context of my example T. I'm not actually able to really display T how T actually exists in the world, whatever that example is representing. So that means it's hard to build a machine learning model from this that actually understands what's going on, or at least approaches understanding what's going on. Instead, it's more inclined to learn by rote, if you like. And in these cases, it may even be biased in ways that we didn't want it to be. What we can also see here is that, essentially more formally, that we're creating another normalization of our data, and an unpleasant one. We're saying, okay, we're taking these table format data, which is in third normal form, and we're trying to translate it down into a single table to represent our data. So, well, when I say table, I mean some n-dimensional array that we can feed into our ML pipeline. So let's just take a step back and see what does that actually look like when we zoom out. So we're going to have that table data. We've got some sort of extract, transform, load pipeline. That's some sort of transformation that's going to get us over to some flat feature data that we're going to want to ingest into our ML model, whatever that ML model looks like. And as an outcome, we get some results. what we also see is that it's very typical. If that ETL, I'm calling it ETL here, it's kind of a couple of things that are going on there. We're extracting data, reorganizing it, and also encoding it into features and doing any normalization or anything like that, all within that one code block, if you like, one aspect of that system. And the trouble with that is it means that when we decide that our results aren't good enough, and that's almost inevitable at some point when we're working on some hard problem, certainly every ML problem I've ever tried to work on, you do, on your first iteration, the results are not what you wanted. So you feed back and you say, well, what could I do about my data? Do I need to change the data that I have? Or do I need to change how many samples I'm taking? Or do I need to change the features within that data, what I actually have exported from my table? Do I need more information? Do I need to display the information in a different way? Am I biasing the machine in some way? And so all of that creates this feedback loop when it comes to the actual work cycle that you're going through. And you go back to this place that you were in before, which is always the bit we like the most when we're trying to do like the least, sorry, when we're trying to do the, unless you've got particular personality traits, most people don't like this bit. They want to get to the machine learning. They don't want to do the data munging part. But they have to go back there every time something is not as they want with the data, with the results and the data loop. Okay, so what could we do to start trying to address this flow from data to transform to model, but then with this cycle in it? Well, what we can also see is that often we're going to use the same data source, or at least some overlapping intersection of data sources, to feed multiple different projects that we're working on. So there might be actually very, very similar ML models that we're using to make two different predictions, but regarding the same domain. A lot of organizations are going to just work within the same domain, so they're always going to have like one particular or a number of separate data sets that they always want to consider. And what we can end up finding is that we have a lot of repeated work, repeating this transformation process to build out both firstly extract the relations that we want and put them in a format that we want them in, and secondly to actually encode those as features for our models. So can we actually abstract this? Is there a way that we can change this to not have to do so much work each time? And the proposal here is then to find something that can sit in between the ML and this transform that we have to do, where we actually mine the relations out of our data in whatever way we need to. Can we add something in there that will give us some common interfaces to work with that makes our life easier? And the idea would be that then, in this case, we can serve multiple projects, multiple ML use cases with the same pipeline. We can just build the pipeline once and then use it, or build the pipeline once and extend it and just reuse it, and just keep building on something we've already got. So what is that abstraction? What is that abstract thing that we want to put in the middle? Well, it needs to be something that's good at being able to store and process relations. So in that case, what we want is we want to move from data and then transform to a database which can actually persist and store some large amount of data, because we may be dealing with a vast amount if our ETL is not actually just for loops, it's actually, you know, a Kafka streaming pipeline or some such. So we actually need a way to be able to store big data here, and we need to be able to store expressive data. We need to be able to store our relations properly there. So if we can make it that far, what does it look like now? Well, now, when we want features for our ML models, we're actually talking about querying the database. But querying the database, we still don't want to then just end up with some flat set of features, because otherwise we've made a better abstraction here of what our data looks like, and we've got the relations captured, and then we're throwing that context away by making the data flat. So what we really need is we need to be able to also do our machine learning over the native graph. And there's this huge ecosystem. Graph learning is having this huge uptick at the moment, and because of the ubiquitous usefulness of being able to do this. And we see, in particular, I think the most widely adopted now is PyTorch Geometric, which offers a whole ream of these graph learning methods that we can apply directly over the graph without flattening the structure, so we can keep all that context that we have in the graph in place and learn from it directly. Well, how is that working? Well, the idea is that we use something like message passing, so that passes signals in between the elements of the graph, and while it does so, it updates the state at each node and edge, for example, of the graph, and maybe we let that message passing run for 10 iterations, and at the end of that, we test and see, okay, does the representation at this node indicate that it should be classified as A or B? This is the very, very broad spectrum of roughly how those things work. But if we want to achieve that, we still haven't got everything we need here, because we need to learn the kind of message we're sending. We can't just send like symbolic messages and say, we don't know what to send across these messages. We need the ML to learn what messages to send and how to update the representations of each node and edge as it goes. So how is it going to do that? From what? From what are we going to actually create these messages we pass around the graph? Well, we don't want just homogeneous data that we're going to pass around. We don't want, and this has actually been, I think the space is rapidly moving towards heterogeneous data, but certainly in the early days of graph learning, what we saw was examples like protein-protein interaction data sets, where every node is a protein, every edge is an interaction. Now, that's a little bit on the boring side, because most data that we're dealing with doesn't really look like that. We have heterogeneous data with all sorts of different types. And what we want to do is we want to be able to ascribe some vector representation, some numeric vector representation, to all of the nodes and edges in our graph. Why? Because that's the input that we need for graph learning methods. Some node edge basic graph with feature representation for all of its elements. And that's what's going to let us build up those messages. That's how we're going to derive the content of those messages. So how do we actually capture this context? Well, that's where TypeDB comes in. So we use TypeDB as that expressive graph format database that we transform our data into, and then from there, at that point, we must already have the context present in the graph and in a strongly typed way, because we know that TypeDB will not allow us to input data without, for example, adding the type. It's in the name, right? So we know that when we have this graph on the left, when we actually are forced to input that into TypeDB and apply our knowledge of what's going on in the data from those messy CSVs we have into a knowledge model, we ascribe all these different types to the different nodes and edges. So for example, we see that this is actually a person entity which is playing roles in 3 different relations. It's both a buyer in one transaction, a seller in another transaction, and is a teacher in a teaching transaction. Teacher in a teaching relation. So already, just from having that type information enforced, we can see that we know, and we are guaranteed to know, a lot about the data that's going on there in this graph. And if we're, say, working with a customer 360 use case, where we want to understand the customer, this already tells us a lot. This may already help us profile what that person looks like. So that's our first step. We want to capture the information in the model. But that's not the only kind of information that we want to be able to capture. When we're dealing with graph-like data, and we've normally extracted that from tables, we're typically, almost ubiquitously, going to also have some set of values ascribed to our nodes in particular, our edges too. And what do those things look like? Well, if we just go to a very most standard graph representations, have the ability to add some dictionary or map of values to a node or an edge. So in this case, for example, we might have a row of a table that we've ingested that was a person. And that person had held against them a name and 2 addresses. So we had to call them address 1 and address 2 in those table formats. Otherwise, we needed to have a whole new table and join to that table. So we've got address 1, address 2, email 1, email 2, date of birth. All of these have different value types. So some of them might be numeric, some of them might be string dates. And we see that there's a one-to-many relation going on between the type of entity we're discussing, so a person, and the different properties that it can have. So when we move over to a TypeDB native representation of this, we aren't allowed to store properties, values against an entity. We must instead, we are enforced to use an attribute to represent each of those properties. And it actually makes the representation really natural, because it means that we now have a person entity, and that person entity has a name, it has an address, it has another address. We don't have to namespace these as address 1 or address 2, we just have this very natural way to represent the same thing twice. The same goes for the emails, we have 2 of those, and we have a date of birth. And then what we see is that we pass messages along the edge that separates these nodes. Right? Because now our properties, what were properties or values that we held in our tables, become first-class citizens. They become nodes of their own. And this is what lends TypeDB to actually be a first normal form data system. So given all that, we can now see, and I hope that it starts to ring with some sense, why we would want to move towards displaying our data and capturing our context in TypeDB. So we would have our initial data, so that might be, it could be any number of different formats, but it's probably messy, right? Or it's not representing the context the way you want it to, for you to be motivated to use this pipeline. We transform that so that we're dealing with TypeDB now, and that means that we have both the strict interface at the input and the output. We know what TypeDB can take in, and we know what it will give us out. So then what we're going to do is we're going to use queries to extract graphs that we can learn over. But what I said before is that we're going to use the queries to extract graphs as our features, and we need these features somehow. Well, we need these feature vectors attached to the graph. Well, how? Actually, we're still missing a step. How are we going to do that? We can't just go straight from, expect to go straight from the output from TypeDB, you know, the query in its raw format, into our ML pipeline. There's going to be something that happens in between. So how do we do that? How do we bridge that gap? Time for a thinking emoji, right? So this is to remind you, this is the kind of model we have now, where we've got entities playing roles in relations. Relations could have multiple role players. Entities, relations, owning attributes. So overall, this actually gives this kind of a diagram for what's going on. It may look a little bit complicated at first glance, but it's actually not at all, because we see that we have the same type of edge. We have only 2 types of edge here. We either have has edges or role edges. We see that all of the nodes, so entities, relations, attributes, can own an attribute. Any node could own an attribute, okay? And any node could play a role, because we see that relations can play roles in other relations, attributes can play roles in relations, entities can play roles in relations. Okay, so actually nodes all can do quite similar things in that regard, in those 2 regards. All right, let's hold on to that. We also see that attributes are first-class citizens, they're nodes, and carry just 1 value. Right? And it's strictly 1 value, no more, no less. Okay, so that's good. We also know what format we're dealing with there. And thanks to the type system, we know that all of these types of node must contain a type. So there you can see that I filled in this diagram saying that we've got relations always have a relation type, attributes have an attribute type, entities have an entity type. They're all types of thing. And then we've got these two types of edges that are possibly going around. Now, the gap we're trying to fill here is once I've got an answer to a query, how am I going to get a numerically encoded into feature vectors kind of graph that I can then use in something like PyTorch geometric, that I can feed into the ever-increasing number of pipelines that are available and tools that are available for native graph learning. That's our aim here. And what we can see is, well, naturally, that very large body of work that's being done by the research community is not tailored to this specific knowledge model. Well, what model is it tailored to? Well, a node edge model, the textbook standard model for a graph, where each node and edge has some feature attached to it. So what we want to do is we want to get to a node edge representation. And we can do that if we consider all of these entities, relations, and attributes as the nodes of our graph in TypeDB. And then we consider that we have edges that are also either has or of a role type. We can actually quickly arrive at this, if you like, summary format of the graph, where each node has a type and optionally now has a value, because if it's an attribute, then it has a type and value. If it's an entity or relation, it doesn't have a value. And then this edge, which is either a has edge or part of the hierarchy of roles. So this is able to capture all of the information that we've put into our TypeDB instance for our project. But what it's done is it's done it in a way that we know is type safe. We know that because we came out of TypeDB, we actually have a very well-structured graph here, but we can have it in a different format, for example, Network X. We can export this into a format that's ready for us to use in Python, the language of choice at present for ML, to feed directly into these frameworks that are available for us to use. Okay, well that sounds good. But James, what you still didn't actually tell us was anything about how we're going to actually get to a vector from this. How are we actually going to arrive at that? Okay. We know we want to get to this representation. We know we need to vectorize some numeric representation of this. So we see that what we need to do is to create embeddings. So embeddings is to be able to, if anyone's unfamiliar with the term, is to be able to find some translation from something that we're trying to understand into some vector space. So we're trying to embed this in the space, and we want to understand what this vector space needs to look like to well represent all of these concepts that we're trying to understand and trying to encode. So what we want to embed is all of the different thing types that we have in our graph, and we also want to embed the role types, and also, as an aside, has, just as a type of its own. We also need to be able to embed values. We need to understand what the values look like compared to one another, so we probably want some vector space to be able to contain that. How do we do this? So we need this vector space both for the edges and for the nodes. Well, this means that we need some method of embedding the types, and the type embedder is all we need actually to embed the edges here, because we can treat has as a type, and then roles are always in a type hierarchy, so they are always typed, so we just need the type embedder. I don't know what that's going to be like yet. Maybe we'll look at that next slide. So we need a type embedder for that. For the node, we need two things. We need to both embed the type, and we need to optionally embed, but depending on whether it's present or not, the value. So I'm not going to go into, in this talk, I'm not going to spend any time on the value embeddings. It is actually quite interesting. There are some challenges there, but what we do is quite simply we ask a user to ascribe, well, what are the characteristics of this attribute that you've got in your knowledge base? Does it describe categories? is it continuous instead? Is it a continuous numeric value, or is it a string? And then we can dispatch the value that we find, because we can get the users can dictate this on a per type basis and say, oh yeah, in my knowledge base I have a name, so that's a string, so embed this as a string. Or I have an age, so that's a continuous value, so embed that as a continuous numeric value. And then we have we can build out these components, which we already have, to be able to embed these different types. But the type embedding, given the subject of the talk and the novelty of our shift over into talking about TypeDB, is where the real interest is here, I think. Because we have a question, how do we embed these types? Well, I want to first show you the simple way. The simple way is, okay, I have some node that I want to represent. And to start with, my representation is that I just have the value motorbike for the class that we have here, the node that's in front of us. And there's no value ascribed to that, because that's an entity and not an attribute. Okay, based on this, well, first of all, I need to know what are the types that we have available to us in the database, because how I'm going to create this embedding space is actually dependent upon which types it is that we have available. So what I want to do is I want to start by, when I'm trying to create this embedding of the graph, I want to enumerate all of the types that I have in the graph. So, for example, if we have vehicle, road vehicle, car, motorbike, air vehicle, plane, this gives us 6 types that we can index just between 0 and 5. And then we say, okay, well, okay, I wanted to embed this particular node that had type motorbike, so I can look that up in the index, and I realize that's index number 3. And then what we do is we simply use, out of the box, I told you this was a simple way, okay? We simply use the out-of-the-box embed methods that are available both in TensorFlow, in PyTorch. I don't know if Jax is going to add one as things go on in Sonnet. You have these embedding methods that are available to you that allow you to, this is a very common task, basically being able to categorically categorize with an embedding. So we can create this embedding space, and one of the main parameters you're going to need to provide for that is how many categories you have. And so we've got this indexing sorted, we know how many categories we have, so we can create this embedding space. And from that, when we want to then embed this one example, we say, okay, go and do some embedding lookup for the given value that I have. Look up in the embedding matrix I have the value 3, because this is the index of the type that we're using. We go and look that up in the embedding. We say this is the tensor that currently represents motorbike, because that's index 3. And so then we can pass that downstream and start using that in our pipeline. So remember how this fits into the graph. This is one of the 2 vectors we need to represent a node, and it's the only vector we need to represent an edge. So once we have these tensors, they feed into the graph that is our example, which feeds as our input to, for example, our KGCN downstream, some sort of graph convolutional method that we're going to use as our learning method. And then the important bit to remember with these embeddings is that when we then back propagate through the neural network, these are tensors that we held on to. These are embeddings that are going to change. We haven't chosen them from the start. So we've just said, index number 3, that's the tensor for a motorbike, and then the back propagation is actually what's going to tell us what that embedding, what the values of that embedding are actually going to be. So we can actually train this end to end. We don't have to first embed the types and then feed it into the network. We can let the network back propagate into the embedding space. So this is great, and this is actually something we already have implemented in KGLib. Like I said, it's very simple actually to embed this. I've kind of blown this slide out of all proportion for how complex it is. It's really not too bad to just be able to take this strong typing and always know that we can derive a feature vector from it to ascribe to our nodes and edges. What about where we want to go next? Well, we want to take the type embedding that we're going to be doing to the next level. How can we do that? Well, what's the scope of what we'd like to achieve with that? Say we take the hierarchy we saw just now, and I just show you a part of that, where we have vehicle as a type, road vehicle as a subtype, motorbike and car as subtypes of road vehicle, and then we have a lot of instances. You can see them with the ISA edges. So motorbike, there's 2 motorbikes there. They are of type motorbike, and there's 4 cars. They are of type car. Now, if I want to be able to represent a motorbike, one of the things I would like my learner to be able to understand as it goes is I may have a disproportionate amount of cars in my data set compared to motorbikes. But I would like, for a small number of examples of motorbikes, for my learner to be able to transfer its understanding of what it is to be a car. The bit that is relevant to being a motorbike, I would like it to understand that. How do I make it understand that? Well, because if we know that we have this type hierarchy where motorbikes and cars are both road vehicles, and road vehicles are all vehicles, all along it's been being told these are examples of vehicles and road vehicles. Right? So if we just do what we saw on the last slide, we don't learn anything between these 2 types, which we would like to. So we want to be able to augment that understanding. How do we do that? Well, first things first, we need to query for the types that we have that supertype what we're trying to embed. So in this case, we have motorbike. So we then going to automatically, of course, make a query to ask us for all of the supertypes of motorbike. So in this case, what we're going to get is motorbike. So actually, in a strange feat of logic, it's actually true that motorbike is the supertype of itself. It should be in the results there. Then we see road vehicle, vehicle, entity, and thing. So this goes up even beyond what I've written in the hierarchy there on the left, because vehicle is naturally an entity, as we've represented with the block, and entities are all things. So we find all of these things are the supertypes of what we have available. Now, the trouble with this is if we draw out the embedding, you'll see that here I've added thing and entity as well into what we had on the last slide. We've now got a bit of a puzzle on our hands, because what we want to do is actually to embed more than one now. We know that it's actually all of these things at the same time. Now, I think there's probably quite a lot of ways that we could approach this, because what we need is we need a way to be able to arrive at one fixed size vector representation, regardless of how deep our type hierarchy is. And also, we need to capture the meaning as best we can from the data that we have available to us. And we've pondered, this has been an ongoing thought exercise for a while on how to do this. And I think the first thing that comes to mind is to build like a recurrent structure, where regardless of, you back in thinking like RNNs. So if, for those hopefully familiar with the idea, where we move from one state to the next, and this is classic stuff for NLP, where we have a arbitrary length input. All of those kinds of methods are favorable in this particular case, because we have an ordering, and we also have an unknown length. But actually, I think that the method that we should really be looking at, which has the most fanfare at the moment, is self-attention. So for anyone not familiar with self-attention, please go and give it a Google. The paper you're looking for is Attention is All You Need. And so in brief, because I'm not going to go into it any further than mentioning that I think this is the best solution we have here, we're going to need to do some more thinking before we actually manage to integrate that properly into this pipeline. But the idea of self-attention is that it's able to ascribe a weighting for the contribution of each of those vectors to one final vector. So essentially it can encode and understand what priority should I give to vehicle versus road vehicle when describing a motorbike. Is it 0.9 of the contribution of road vehicle, or is it 0.3? Because actually, for my use case, cars and motorbikes are very dissimilar. So this is the kind of direction we'd like to move in, and I hope you can see that this can be really powerful. If you have a rich hierarchy in your data, this is really giving us the ability to make our machines understand way better what's going on, and we know that we have this guarantee that everything's got this type information. Now, to that end, I want to make this point as well. Anyone who's done a session with me knows that we talk about modeling choices a lot, because when we have this expressive way in TypeQL to model systems, we want to try and actually make sure we're using it correctly. And what this slide is really important, because it displays how it's not only a matter of just us as programmers getting an easier life out of using the tool properly, but actually our machine learning models can do better for it. So on the left we see a model where I've got it wrong. I say that I've got a person type, and there's two subtypes that a person could be. They could either be a teacher or they could be a buyer. Well, the thing is, it's possible to be both. A person could be both a teacher and a buyer. Now, maybe you've got data sets where they don't overlap, and you're trying to do your customer 360, and you've either got buyers or you've got teachers coming along to your shop or whatever it is, right? And in this case, your hierarchy is broken, because you can't be both, and you can't transfer a good understanding of what it's like being either at the moment. You're just describing what it is to be a person. So instead, we actually need the right-hand side model in this case, where we're saying a person is a buyer because we're aware that they took part in a transaction. They could also be a seller. They could also be a teacher. And how does this look when we actually have an ML model that's processing this? Well, the encoding of the types happens on the edges, so as well as on the nodes. So we see that teacher, buyer, and seller are all also going to be embedded, and the messages passed around this graph as they arrive at the person need to take account of the fact that that role information has an embedding that influences what that person looks like. So if we want to know, is this person likely to buy from us, we want to classify that. That can be taken as input just fine. Okay. So, on graph embedding, let's remind ourselves where we got to. We've got as far as being able to understand how we can embed a graph of nodes and edges, where the nodes and edges both have types, and the node optionally has a value. And this is an abstract format of the of the graph that we have in Kraken, and is ready for us to translate into an ML framework for use downstream. So what we've got is a graph where we've got a vector representation at all nodes and edges that allows us to create these messages to pass around. Now, what I want to do is describe to you how the whole pipeline starts to fit together. We start off with this data that we've got. We've got that in a tabular format somewhere. SQL, CSV, it doesn't really bother us. Because the main thing we're going to do is, through whatever means, whatever scale it is that your organization is working at, or whatever scale your data is at, we're going to transform that data over into TypeDB, so that we can make the most use of an expressive language to capture the context and get the type safety of knowing exactly the format that our data is in when we move it over into that graph. So then we're going to be dealing with entities, relations, and attributes. So from that point, we're moving on to try and extract the features that we want for our downstream learning. So that means we're going to have some set of queries that we're going to make using TypeQL against TypeDB. This gets us back some sets of answers that we actually need to encode into a node edge representation, where we have, as I've already said, we have the thing types, the edge types, and the values. And this is typically going to be in Network X, this quite ubiquitous graph language that we have available in Python. And so this step, quite banal because it's just a translation of entities, relations, and attributes to nodes, and the edges in the TypeDB graph over into ordinary edges, if you like. But then the exciting part is happening here in this embedding step, where we have these different types of embedders that we're using according to the values that we see. And then we also have an embedder for the node types, an embedder for the edge types, to be able to transform those over as well. And this is, as we said just now, this is crucial that this is actually something we can backpropagate through. So this is actually a trainable part of the pipeline, which I think is really key. Now, and I think that's really key because a lot of the time there's work going into generic graph embeddings, and I would urge people to be cautious when using generic graph embeddings because they may be totally missing out the context that's actually important for your use case. If you train an embedding specifically for your use case and then use it downstream, you sort of do the training cycle and then use it downstream, that makes sense. But in this case, what we want to do, which we think is the most adaptable, is actually connect that to your whole downstream pipeline, and then you can backpropagate all the way through. So following that, naturally we're going to lend over to our machine learning methods that are downstream. So this could be, for example, the knowledge graph convolutional networks that we've already published. And this is, we've got this on in KGLib. I imagine if many of you who are attending today may have heard me speak far too long already on that subject. If you haven't already, then you can check out the talks that we have online regarding that. So that goes into the detail of this thing I've been alluding to on how do we do message passing in machine learning. And that is, particularly check out the talk from Cosmos last year, Cosmos 2020. But there's a family of other methods that we would like to be able to swap out for the KGCN to change the bias of exactly how we're doing that message passing, depending on exactly the data that you're actually dealing with. So that's up for customization. Now, what is it that we've actually achieved by putting together a pipeline like this? Because it looks a little bit onerous to start with. Well, the first thing is that we hope that you will find that from this, you just end up needing to do ETL once. The most painful part of the data munging process is something that you can just do once, and with a good representation, you're aiming to build that representation out, and once you have it, that's reusable for lots of different projects, right? You create a generally useful knowledge graph that you can query just to answer very simple questions and to understand your data. In fact, TypeDB in this context, the way I see it, starts to play the role that something like Pandas does, actually, in the machine learning community, where you want to be able to cut and chop your data in any which way that you'd like to. And in fact, you could throw away everything after the queries part of this pipeline and just deal with tabular data if you wanted to, and just gain the benefit of that broad knowledge base and being able to query flat data to your heart's content and chop and change your data using queries. So beyond creating a generally valuable knowledge graph, what we also see is that the feedback loop that we gain when we decide that our results are not up to scratch only means that we should change from the queries and downstream. Unless we need to go and fetch more data, which of course is possible, we should just be able to go back and change the queries that we're actually using to extract the data we're learning from. Now, This has certainly been true when we've been using the KGCN, this KGCN pipeline in anger, and I hope that anyone else who comes along who is going to use this is going to find the same. This really changes the dynamic on how you're using things. And following that, we see that we've got this big block in pink, which is that having abstracted how our data looks and enforced the type where types and values can occur in the data, this means that we can now build generic embedding tools. And that's actually what we've already done. So if I walk you through the pipeline, your data comes in, then the bits of this pipeline you actually need to touch are the ETL, because we don't know what your data is going to look like, so we're going to need to, and you need to look at projects like Grammy to help you do imports if you need help there, to get to TypeDB. You're going to need to write your queries. I hope you don't find that onerous. And then you're going to need to customize and change the model that you're going to use in some way, because that's the game in machine learning, right? And then KGlib wraps up the graph extraction from TypeDB, and also the embedding step, and potentially some ML implementations for the message parsing. But crucially, the encoding and embedding steps that get you to this point where you have a node edge graph with your features attached to them is all taken care of by KGlib for you. That's the ambition for that project now. That project is not, we need KGCN to showcase how it's possible to do message passing over the graph. That's now very popular. So now what we want to focus down on with that repo, and thank you so much to those who have already been collaborating with us and contributing on that, you know who you are. We're really moving in a more modular direction with that just now. And the last and really key point is that what we can hope to do here with these advanced type embeddings, with the advanced type system that we've got in the database, is to improve the machine's understanding of the domain that we are working over. As we can see, by being able to build these complex embedders and by being able to trust that all of the information we have has these types. So thank you all so much for listening. I hope that you've taken away how we see the scope of being able to integrate TypeDB, TypeQL, machine learning all together to make a really robust pipeline that's usable for anyone trying to work over complex relational data. Okay, so if there's any questions, I don't know if we have time for questions at this point. No, then we're going to move on. So have a great rest of the day 2 of Graken Orbit. I hope to see you all again soon. Thank you.